Okay, welcome back. We're going to continue talking about, excuse me, Bayes' theorem and Bayesian inference today. So, if you recall from last time, the outline of what Bayes' theorem says is that it takes as its input, right, a bunch of hypotheses we might have about the world, right? So, in most of the cases we'll look at here, we're just considering two hypotheses, but of course that could be any number of different theories you have about how the world works. And it gives us a way of assigning probabilities to each of those hypotheses in the face of some set of observations we've made about the world. And we're referring to that as data, or D here. And so what Bayes' theorem says is that given those inputs, right, we have a bunch of theories we're trying to decide between, and we have a bunch of observations that we've made about the world around us. Uh, the way that we should assign probabilities to each hypothesis, and this is what we're trying to get out of the decision making process, is the probability of each hypothesis given the data that we've observed. This is referred to as the posterior. That's what we want to get eventually. How are we going to do that? Bayes' theorem says that for each hypothesis, the probability of that hypothesis given the data, conditioned on the data that we've seen, is proportional to two things. One of them is the likelihood of the data under that hypothesis. This is how likely or how probable it would be to see data like the kinds of data we've seen if the hypothesis were true, right? So that's going to obviously differ for different hypotheses. And also, it's proportional to the independent or prior probability of the hypothesis. And how do we get information about the prior probability of some hypothesis? Well, it sort of depends on what kinds of hypotheses we're talking about. But the idea here is that we don't just go into every situation where we're observing the world blind and forget everything that we already knew about the world. Instead, we incorporate information that we already have about the world and then update it using the data that we've seen. And we combine these two sources of information in particular ways in order to apportion probability or likelihood to different theories we might have of how the world works. That's what Bayes' theorem says. And this part, the likelihood part, updating our assignment of probabilities to different hypotheses based on what the data seem to be telling us, that one's pretty typical of every approach to science or every approach to inference that's a systematic approach. That's pretty normal. This is the part that Regier and Gahl actually focus on. But that's really not the part that's novel about Bayes' theorem. What's actually more distinctive about Bayesian reasoning as compared to maybe some other ways of thinking about science is the importance assigned to the prior probability of hypotheses. That's sort of the gimmick or the interesting thing about Bayesian reasoning. And it plays not very much of a role in the Regier and Gahl type argument, but I think it's still important to focus on when we're thinking about what Bayesianism is as a conceptual framework. It's a way of apportioning different amounts of importance to the data that we've observed, for sure, but also to the independent probability of different kinds of theories about how the world works, right? And so, while the prior is not going to play a large role in the Regier and Gahl example, I still want to focus on it a little bit here. And in particular, because it has some importance for cognitive science as a whole and for just ways of reasoning about the world. So let me briefly recap a very simple linguistic example that we went through last time. I would call this a toy example. This is the example of how does a speaker resolve lexical ambiguity? That is, basically homonyms, two words that sound the same. The example I gave from English was the string of sounds pen. And actually, this can have multiple different meanings in English. I've just focused on two different ones here. Pen 1 is a writing implement, right, that puts ink on a page. And pen 2 is an enclosure for farm animals, usually pigs, right? And the reason I picked this example is that I think for most people in this classroom, for the average American English speaker, so on and so forth, that the writing implement is a much more frequent word than the enclosure for pigs, which would be much less common. You don't hear that as much, right? And so what Bayesianism does here is allow us to simultaneously describe why, in a sort of neutral context, where the observations, which in this case are going to be sentences with the string of sound pen in it, In the neutral case where those data don't give us much information one way or the other, we're going to default to our priors, right? So in particular, if we have a sentence that really doesn't distinguish between the two meanings, like, hey, there's a pen over there, um, we're going to default to the fact that usually when we hear this string of sounds pen, it refers to a writing implement and not an animal enclosure, right? So in a neutral context, we're basically going to have not much information at all from the sentence, from the data, because it's not semantically biased towards one or the other. What we have is the fact that our prior probability for the writing implement pen is just going to be much higher than our prior probability for the animal enclosure pen. So Bayesianism can explain that intuition. But on the other hand, when we do have a very biased semantic context, we can overcome those priors and end up with the posterior probability being assigned to the animal enclosure being higher, even though it started out with a lower prior probability. Here's how a Bayesian framework captures this, right? We start again with high prior probability for the writing implement, low prior probability for the animal enclosure. But then we get a sentence like, I put the animals in the pen, right? And now all of a sudden, the likelihood here, how likely would we be to observe the sentence, I put the animals in the pen, if what the person had in mind was a writing implement? And the judgment is that would be extremely, extremely unlikely. In fact, I've put 1% here, but it's probably less than that, right? Whereas, how likely would we be to hear the sentence, I put the animals in the pen, if we're talking about an animal enclosure? Well, much, much, much more likely. And so that's reflected in these relative numbers. Note that I've made these add up to 100, right? As if we were talking about a percentage. This is not actually how likelihoods work, right? In real life, the likelihood of hearing any particular sentence with the writing implement in it is going to be extremely, extremely small because there's a probably infinite number of sentences with that word in it. And the likelihood of hearing any particular sentence with the animal enclosure is also going to be extremely small. But the only important point here is that the likelihood of that sentence with the animal enclosure is going to be much higher than it is with the writing implement. So here I've given them a factor of 99 to 1. Of course, in real life it might be substantially higher than that, but the point stands even if the numbers are made up here. Right? So these don't need to add up to 100. All they need to reflect is that it's more likely to hear a sentence like, I put the animals in the pen, if we're talking about an animal enclosure, than it is if we're talking about a writing implement. Now, what does Bayesianism tell us about adjudicating between these two different possibilities, these two possible words? Well, we multiply these out because the posterior probability of each hypothesis, where the hypotheses here are word meanings, right, is proportional to both the prior probability, which is somewhat unbalanced here, and the relative likelihood, which is much more unbalanced. And again, what we get out of this is not probabilities. These add up to whatever, 1,080. That's obviously not a percentage or a probability. What we're getting here is a measure of the relative probability of these two hypotheses. It tells us that this one is 11 times more likely than this one. Right? And that's basically what we're getting out of this. So showing again that Bayesian inference can describe how people's actual cognition works in real life. At least for this example, it seems to do a decent job. Of course, you need to do experiments on this kind of thing to see how close it really matches real data, but this is just meant to be a toy example. Now, we distinguished earlier between Bayesianism as a normative hypothesis, which pretty much everybody agrees with. That is, Bayesian inference is the best or the most rational way to update our beliefs in the face of new data, versus descriptive Bayesianism, which says that this is how humans actually do inference and decision making. And that's more controversial. I've picked an example here with lexical ambiguity that seems relatively consistent with descriptive Bayesianism. This seems like not a bad description of how people might decide between two word meanings, right? So it captures both the default tendency to default to more frequent word meanings in neutral semantic contexts, as well as the ability for those preferences to be reversed under highly informative data that has a semantic bias to it. Right? This is the basic idea. This one incorporated both likelihood and prior information, and that's how the best Bayesian approaches work. Right? A couple other things to note here. Just like any English string of CVC sounds, there's actually more than two meanings for pen. So just off the top of my head, I can think of pen as a nickname for a penitentiary, which is a kind of prison. It can also be a shortening of the state of Pennsylvania. And I'm sure there's even other ones here that I'm not even remembering right now. So in real life, this isn't going to just be about two hypotheses. We're going to get these columns of numbers for a whole bunch of different hypotheses and be evaluating the relative posterior probability of each of these here. And then, once we have relative numbers here, it's pretty easy to just convert that into probabilities in whatever your favorite way of doing so is. Right? So the examples we'll see with language acquisition tend to hinge around the likelihood factor here. But I do want to focus in briefly on the prior because it's a really important component of the Bayesian framework, and it's really what distinguishes it from other approaches. And in particular, I want to focus in on one case where descriptive Bayesianism runs into trouble. That is, where it doesn't seem to necessarily capture exactly how humans actually reason and make inferences. And these are going to be explicit inferences. So maybe they're just different than all the other stuff we've studied in this class. But it's an interesting test case. It's a useful way of understanding a little bit more what Bayesianism does as a framework. And actually, it turns out to have become sort of strikingly and unfortunately relevant in our recent lives. This is a textbook example that has to do with medical diagnostic testing, and this has been front and center in the coronavirus situation for the last couple months as well. So maybe I'll say a word on that at the end of what we're doing here. The example I'm going to use here, though, is also ripped from real life, and it involves testing for cancer. So in general, for most kinds of cancer, what we have are, first of all, a less invasive and less painful and costly imaging technique that can be used to look for tumors. And then what we have usually is a follow-up test that's some kind of a biopsy, which is more invasive, it's painful, it's expensive, it's actually risky, but it gives better certainty about the results. And there's been a lot of debate in the clinical world about how widely we should be deploying these imaging techniques because they're far from perfect. Right? And so a classic sort of intro to statistics example of where Bayesianism fails as a model of human intuitions comes from these kinds of diagnostic testing scenarios. And I'm going to use the mammogram as an example just because this is actually a real life example where these kinds of debates have come up. So what is a mammogram? A mammogram is a way to test for tumors in the breast through imaging. So it's a non-invasive procedure. It's not painful, it's not medically risky, and it's not that expensive. And so it's sort of the easy way to test for tumors in the breast, and it uses imaging. So what do I mean by saying it's not perfect? Well, in both perception and in clinical medicine, we talk about two ways of quantifying how good a test is or a decision is. And these are, in the medical world, referred to as sensitivity and specificity. The language in perception is a little bit different. The jargon's a little bit different, but the ideas are exactly the same. So in medical terms, we'd say that the sensitivity of mammography is around 80%, meaning that if you have a tumor in your breast, there's an 80% chance that the test will correctly tell you, hey, you have a tumor. And so in perception, we usually refer to that as the hit rate, but in medical science, it's referred to as sensitivity. Confusingly, in perception, we have another quantitative measurement that's referred to as sensitivity that's not the same as this. Let's put that aside for the moment. It's confusing. In medical science, this is the sensitivity. So it's like the true positive or the hit rate. In medical science, they also talk about the specificity of a test. And the specificity of a mammogram is around 90%. So if you don't have a tumor in your breast, there's a 90% chance that the test will correctly tell you, hey, no tumor. Now, in perception, we often talk about the complementary 10% rate, which is the false alarm rate or the false negative rate. In medical science, they usually talk about the specificity, meaning the true negative rate. That said, these are completely derivable from one another. And yeah, so these are the important properties of this test, right? This is going to be the data that we get back, and we're trying to decide between hypotheses. You have a tumor in your breast, and you don't have a tumor in your breast. The data we're getting is a test result, right? And here are the properties of the test. If you do have a tumor, there's an 80% chance that the test will catch it. And if you don't have a tumor, there's a 90% chance that the test will catch that you don't, right? Also, what Bayesianism tells us is that it's actually really important to know how common breast cancer is in general, right? So the general prevalence of breast cancer is about 1 in 1,000. Right? Here's the first question. Don't try to do math here. Just look at these numbers. 80% chance that we'll catch the tumor if it's there, 90% chance that we'll correctly say there's no tumor if it isn't there. 1 in 1,000 people has breast cancer. I think that's per year maybe, but I'm not totally sure. So here's the question. If you go to the doctors and get a positive test result on your mammogram, how likely is it that you have cancer? Actually, what this is really testing for is a tumor, not cancer, but ignore that. Let's say, how likely is it that you have a tumor? What's the probability that you have a tumor in your breast? And you don't have to give a specific answer. Just pick one of these ballpark figures. Well, given that positive test result, my mammogram came back positive. It's A, pretty likely that I have cancer. B, about half and half. Or C, pretty unlikely that I have cancer. And you don't have to tell me your answer or anything. Just keep that in mind for a moment. And I'm going to ask you a similar question. But this one's about the flu. So let's imagine that there's a very similar test for the common flu. Just like the mammogram, the sensitivity is about 80%. So if you have the flu, there's an 80% chance that the test will get it. If you don't have the flu, the specificity is around 90%. So if you don't have it, then the test will 90% of the time correctly tell you that you don't have the flu. Unlike breast cancer, the prevalence of the flu is about 20% in the general population. So breast cancer was much lower. For the flu, it's much higher. And same question here. If you go to the doctor and get a positive flu test result, how likely is it that you have the flu? Now, we're not only interested here in the answers about how likely each one is. The main question here is, did your answer change between these two questions? Did you give a different answer for breast cancer than you did for the flu? And what Bayesian reasoning tells us is that you should have. Why is that? Given these positive test results, the actual chances that you have breast cancer are less than 1%. But the chances that you have the flu are nearly 70%. So it's more likely than not that you do have the flu. What we're trying to decide here again is probability of hypothesis 1, you have the flu. Hypothesis 2, you don't have the flu. Hypothesis 1, you have breast cancer. Hypothesis 2, you don't have breast cancer. Those are the hypotheses we're evaluating. The test result is the data here. Why is this working out this way? The answer is the base rate, the prior on having the breast cancer versus having the flu. And why do these percentages work out this way? Because breast cancer is really, really rare, and the flu isn't really rare. It's really common. The fact that we've been given a test and it's produced some kind of data for us to make a decision about doesn't change that fact, or at least if we're reasoning properly and rationally, it shouldn't erase that fact entirely, right? We knew before we ever tested anybody that it was way more likely for somebody to have the flu than breast cancer, and that's still true regardless of how the test comes out. How does Bayesian reasoning capture this? Well, the likelihood figures here are going to be exactly the same because I rigged the example so that the data, namely the test results, are telling us exactly the same thing, right? So the question here is, how likely is a positive test result if you have the disease? Oh, sorry, that's not right. How likely is the positive test result given hypothesis one, you have whatever disease we're talking about? It's 80%, right? That's the specificity. Excuse me, that's the sensitivity. How likely is that positive test result if you don't have the disease? Well, it's about 10%. That's the false positive rate, or the complement of the specificity. And this is exactly the same for both tests because I fixed the example that way. So the data are telling us the same things in the two cases, and many people have the intuition that therefore it's equally likely in the two cases to have the disease. But what Bayesian inference tells us is why that's wrong. In fact, the prior still matters here. And what's the prior probability of having breast cancer? It's about 1 in 1,000. What's the prior probability of having the flu? It's about 1 in 5. Right? So when you multiply these out, what you find here is that it's true that the likelihood favors you having breast cancer in the mammogram case, except that given the strong prior against it, we know that there's likely to be more false positives in the population as a whole than there are true positives. And so even given that positive test result, your chances of having this disease are extremely low. Versus the flu, the test results, the data favor you having it, and the prior slightly disfavors that, but not anywhere near as strongly. And so it's extremely likely that you do have the flu given that test result. Here's another way of thinking about this. If the false positive rate, which is about 10% down here, is higher than the prevalence of a disease in the population, which here is 1 in 1,000, then almost all of the positive test results you're going to see are going to be false positives and not true positives. Why? Because people with positive status are extremely uncommon to begin with, and if the rate of false positives is higher than the rate of the disease in general, almost all the positives you see are going to be false ones. For the flu, where we've decreed that the rate of false positives is lower than the prevalence of the flu in the population, that reasoning doesn't hold, right? Most of the positives you see there are going to be actual incidences of the disease. So there's a couple observations here. One of them is that people often have trouble with this kind of reasoning, and this includes medical professionals. It includes doctors as well. Doctors are not particularly good at doing this either, despite their years and years of training and experience with such diagnostics. And this suggests to us that at least for this kind of a decision process, Bayesian reasoning is not doing a good job of capturing how humans think about these problems. So descriptive Bayesianism seems to run into some trouble here. It also tells us that nonetheless, the Bayesian approach is strictly better. It's optimal. And so this is actually a problem. We need to think about these tests in more Bayesian terms because it gets at the nature of reality better than our naive intuitions, which are actually doing a really bad job of approximating reality. So thinking about this a little bit more, just trying to explain this result, it's kind of important. If you understand the base rate fallacy, which is what this reasoning mistake is called, then you pretty much understand the entire Bayesian framework. So I'm going to spend a little bit more time on this. Here's a way of putting this. Before you ever walked into the doctor's office, you were 200 times more likely to have the flu than you were to have breast cancer. Right? So before we knew anything about your test results, before we'd done anything medical to you, it was already the case that this is a highly asymmetrical scenario where you're 200 times more likely to have the flu than breast cancer. What does the positive test result do? Well, it changes those numbers a little bit. It's certainly not as asymmetrical now as it was before. So now, what the Bayesian approach tells us is it's only 83 times more likely that you have the flu than that you have breast cancer. But it doesn't completely override the prior. It just gives us a bit of additional information that changes our inferences about the probability of these two things. Right? It doesn't completely erase everything that we knew about breast cancer and about the flu before we walked in that doctor's office. It changes it, but it doesn't erase it. And that's why the prior is important in inferences and decision making. So here's an informal way that scientists have of talking about correcting for this base rate fallacy. So we all have the base rate fallacy inside of us. It seems to be part of human explicit reasoning and problem solving, at least. We're not sure about implicit stuff, but for sure, making explicit judgments and decisions and reasoning, we all have a tendency to make this base rate fallacy and not take prior information into account. And so, a way that scientists talk about this in the scientific context is to say that extraordinary claims require extraordinary evidence. Right? And a way of rephrasing that in terms of priors is that claims with low prior probabilities require much stronger likelihood evidence to be judged probable than claims with higher prior probabilities. In our specific example here, the proposition or the theory or the hypothesis you have breast cancer is a fairly extraordinary claim. Right? We know that only 1 in 1,000 people have breast cancer, whereas the hypothesis you have the flu is much less extraordinary. That's a pretty normal thing for somebody to have. And our sort of fault here is that when we look at an experiment or a diagnostic test or some sort of observation of data from the world, we tend to privilege that to such an extent that we don't think the prior matters. That's what the base rate fallacy is. What Bayesian reasoning tells us is that we ignore this distinction between a priori probable hypotheses and a priori improbable hypotheses. We ignore that distinction at our peril. This has flown into the headlines in the last month with regard to the COVID-19 crisis because there's been a number of different diagnostic tests developed, and they all have different sensitivities and specificities. But one of the most relevant and interesting ways this has come up is with so-called serological testing, which means testing people to see if they have antibodies indicating that they've been infected with the COVID-19, with the coronavirus that causes COVID-19 at some point. Right? So the idea here, this is not a test for whether you have COVID-19 right now. It's a test for whether the virus has been in your body at some point, and we hope maybe that if it is, then maybe you have immunity. So this is super important, and there's been a bunch of studies that have been randomly sampling, or as close to random as they can get, sampling people on the street, trying to sample large portions of an entire population to try to find out, well, how many of us have already been infected and don't even know it? The higher that number is, the safer we probably are. Because it means that A, the disease is not as deadly as we thought, and B, it may have spread much further through the population than we knew and might therefore have almost run its course, right? So these are super, super important real world claims. And a number of those studies have built models of, well, given the test results that we got when we did these antibody tests, here's what we estimate the true prevalence of having been infected with this coronavirus is in the population. And some of those numbers have been orders of magnitude higher than what we've actually been able to confirm through positive disease tests, right? So this is a giant finding, if it's true, that actually in Santa Clara County, California, maybe 4% of all the people in that county already have antibodies to the virus, even though we've only confirmed infection in less than 1% of them. There's been similar things done in Chelsea, Massachusetts, near my hometown, and in other places in the world, and they're coming up with these results that way more people are testing positive for antibodies than we knew about before, or that we estimated before, so maybe we're all safer than we realized. There's also been a backlash against those models correctly. Why is that? Well, a number of these statistical models that researchers are putting out about these antibody tests make the assumption of 100% specificity, That is, that these antibody tests don't have any false negatives. And that's based on very shaky evidence. Here's why the false negative rate is super important. Excuse me, the false positive rate is super, super important. As we saw earlier with these diagnostic tests, if your false positive rate is lower than your rate of infection in the general population, then you're going to get relatively meaningful results out of your diagnostic test. This is the flu case where, 20% of people have the flu and the false positive rate's only 10%. Therefore, we're getting lots of useful information out of this test. For breast cancer, on the other hand, if your false positive rate is higher than the rate of infection in the general population, so here the false positive rate is 10%, but the prevalence in the population is only 1 in 1,000, well, now we're not getting very much information out of that positive test at all. Most of the positives that we're seeing are false positives, right? Not true positives. Therefore, we're wildly overestimating the prevalence of this disease when we don't take priors and false positives into account. Now, if those serological tests for antibodies with regard to the coronavirus have a lower false positive rate than the rate of infection in the general population, then great. It turns out that we have learned that many more people have already been infected than we realized. But if they have any kind of appreciable false positive rate, if it's higher than the rate of COVID-19 infection in the population, we're going to come to unbelievably mistaken conclusions, and it's going to be disastrous for public health. So this has been a raging debate in the medical and statistics community. How high are the false positive rates for these serological tests, and are they higher than the prevalence of COVID-19 itself, right? So our best estimates from places that have been tested where the epidemic has raged through, our best estimates are that the rates of infection in the population are below 1%. So if the antibody tests have a false positive rate that's greater than 1%, then all of the data from these studies are garbage. The vast majority of those positive test results they're seeing are going to be false positives and not true ones. So the base rate fallacy has raged into the scientific community this month with regard to COVID-19, and that's just one way in which it comes up. It's come up for several other kinds of diagnostics as well. So I did want to briefly mention that because it's unfortunately become very relevant today. Anyhow, why are we going through all of this? Well, the general lessons here is that one of the central insights from statistical learning and decision theory, that's what we're talking about here basically, is that even if there are lots of theories that could be consistent with the things you've observed out there in the world, some theories will make those observations more likely than other theories will. So that's the likelihood part of Bayesianism, and that's what Regier and Gahl are going to focus on when we talk about poverty of the stimulus in this anaphoric 1 example. With regard to cognitive science and linguistics, what does the prior part of the Bayesian approach tell us about these things? Well, there's a tendency to look at experimental data in our field and try to interpret it in a vacuum, right? So here are the results of the study, therefore that proves this hypothesis. And what Bayesian inference tells us is no, that's the wrong approach to take. You don't look at one study and look at the data from it and decide posterior probabilities based on that one study. You have to incorporate prior information if you want to make a logically and rationally optimal decision about evaluating the empirical support for different hypotheses. So it's not that you can just take the results of an experiment, look at them and say, aha, we know the truth now. No, you have to incorporate those data into your pre-existing knowledge, if there is some, in order to come to accurate conclusions about the probabilities associated with different hypotheses. So that said, we're going to step away from the prior for a moment and focus mainly on likelihood with regard to this Regier and Gahl, Lids and colleagues kind of debate. So with regard to syntactic acquisition, and the particular example we'll be looking at, what are the data here that we give as input to the Bayesian model? What are the observations? Well, this is going to be the primary linguistic data, or PLD, that a child is exposed to. Right? And so that's going to come in the form of maybe utterances or strings of words or whatever, relatively unstructured spoken English utterances that a young child might be exposed to. That's our data, our observations. The theories or the hypotheses that we're trying to evaluate here, or that the child is trying to evaluate, correspond to different grammars, different generalizations that we might believe or that we might come to in order to explain that primary linguistic data. And this is totally consistent with the Chomskyan approach to language acquisition. We get some linguistic exposure when we're young, some primary linguistic data, and on the basis of that data, we build ourselves a particular theory of English or whatever other language we're learning. And the Chomskyan claim is that there's hard constraints on the way this process of inference works. But the focus in this Regier Gahl paper is going to be not so much on the pre-existing constraints, but on data-driven aspects of the learning. What are we going to be doing with the primary linguistic data in order to adjudicate between different possible grammars or hypotheses of how, in this case, English works? So the claim is that the data we're going to get may well be consistent with many different grammars. Right? So if there's more than one grammar that's consistent with the simple cases of anaphoric 1 and the context in which it's used, even if we can't absolutely decide between those because they're all roughly consistent with that data, it's possible that the more complex grammar or the right grammar could do a better job predicting those uses than the wrong one, which isn't learned. If that's the case, right, if we could still make predictions about the relative probabilities of different grammars, even if they're all roughly consistent with the data, then we might not need these super complex lacuna sentences in order to choose the right grammar. So the lacuna in this case was, remember, these sentences where there's a multi-word nominal antecedent like red ball, and the one anaphor is embedded under negation or in a downward entailing context, like John has a red ball, but Susie doesn't have one, where only in a context where Susie is holding a different colored ball, right? That's the lacuna here, which appear to be extraordinarily uncommon in actual child-directed speech. And so this was taken to be a problem for learnability. What Regier and Gahl are going to say is, well, even if you don't get those lacuna sentences, it might be the case that the more complex grammar, where one can be anaphoric to any n-bar intermediate level syntactic constituent, that might still do a better job of predicting the simple cases that we do see than other grammars do. And if so, then we don't even need the lacuna to favor that grammar over the others. So this is their way of trying to explain anaphoric 1 without assuming that people, or namely language learners, first language acquirers, exclude lots of structure independent or flat structure kinds of hypotheses. We don't need to assume that. We can choose the right theory just based on the data. Right? This is their argument. So let's start out with our hypothesis space here. Right? This is which kinds of grammars are we going to entertain in order to explain the primary linguistic data that we've seen. So let's start by saying any of the possibilities that we looked at last time for anaphoric 1 is a possible grammar that the child actually entertains. That's the flat structure noun phrase, where it's just ternary branching, determiner, adjective, noun. The hierarchical structure, where we have intermediate projections that are called n-bars within syntactic theory. And any kind of reference is possible. So let's start with one group of hypotheses where the anaphor 1 refers to an n-bar level constituent. And we'll start with some hypotheses where the anaphor 1 refers to head level n0 constituents. And let's assume that these are all active at the beginning of learning. Right? So this is going to be the hypothesis space that we're attempting to get posteriors on. So the eventual goal here is to get the relative posterior probabilities associated with each of these grammars, where the grammars are hypotheses about what English is like. And let's assume further that learners never see cases of unambiguous multi-word antecedents. These are the super complex lacuna sentences that Lids and colleagues show are vanishingly rare in child-directed input. Right? So what Regier and Gahl say is, okay, fine, let's assume that these are all in play and that we never get the lacuna super complex sentences. Could we still say that one of these grammars would be more likely than the others? Here's what I think the intuitions are behind this approach. In the case where the anaphor 1 can refer to multi-word antecedents, it makes sense that it would tend to be used in situations where a red ball is at issue. But in the case where 1 only refers to noun antecedents, that is the wrong grammar, the fact that we sometimes hear the anaphor 1 when a red ball is at issue can only be a coincidence, right? Because there we could have equally used 1 to refer to a blue ball or a yellow ball or a green ball, but sometimes we're seeing it used to refer to a red ball. And as you see more and more cases like this coincidence becomes more and more striking, and it makes the grammars that predict this less and less and less, excuse me, probable. Right, so let me try to explain this a little bit more concretely here. Here's the formalism that Regier and Gahl use here, and it looks a little bit intimidating when you look at these equations, but it's really very simple. So let me walk you through this. And the first step here is to note that they made a giant typo here, which is unbelievably bad, and I can't believe this wasn't caught before publication. They're talking about the different hypotheses or grammars here, and they're talking about how we're going to get a likelihood for each of these based on the observed sentences. And what they actually mean for this top one is the n-bar red ball, the multi-word n-bar here, within the nested structure hypothesis. So that's a giant typo. This should be the same as this one. Here are the hypotheses they're going to entertain, or the grammars that they're going to entertain. Grammar number 1. We have nested hierarchical syntactic structure, as on the right side here. And the antecedent of 1 is the n-bar red ball. It's this big n-bar. Hypothesis 2. We still have nested hierarchical syntactic structure within the noun phrase, but here the antecedent for the anaphor 1 is the n-bar ball. Right? It's this node here. Hypothesis 3, again, still nested hierarchical syntactic structure. Here the referent or the antecedent for the anaphor 1 is the n0, the head level element ball. And then hypothesis 4 here, we start with syntactic flat structure here. So we have totally flat structure with no hierarchy or articulation inside the noun phrase. And here, the only thing that antecedent that can be the antecedent of that anaphor 1 is basically the n0 level ball. It can't be red ball because red ball is not a constituent in this theory. How are we going to judge the likelihood of each of these of the data associated with each of these hypotheses? Well, first of all, let me note here that what they're actually writing here is a formula for the posterior probability of each of these grammars, because they're assuming that we don't have any strong priors, and so the relative likelihood is going to be just like the posterior probability for each of these. So what they're saying here is the following. We have n number of observations, right, where we're hearing sentences with anaphoric 1 in them. And there's C number of different colored balls in the universe. In real life, of course, there's lots and lots of colors that you can make a ball with. For most of these examples, we're just going to assume that the universe only contains red balls and blue balls, so C is going to be equal to 2 here. Now, regardless of how many different colored balls there are, right, if we hear a certain number of sentences where one clearly refers to a red ball in context, then the likelihood that our nested multi-word antecedent theory assigns to hearing such a sentence in such a situation is always 1. Right? Why is that? Because this theory says that, hey, 1 refers to a red ball. So what's the probability of observing sentences where 1 refers to red balls under this hypothesis? It's 1. It's 100%. Compare this to all the other theories here, which all make the same kinds of predictions, which are different from this one. Under a hypothesis where 1 refers to just the element ball, right, whether that's at the n0 level or the n bar level, well, if we hear that sentence once in a context where 1 actually refers to a red ball, if there's, let's just say there's only 2 colored balls in the universe, a red ball or a blue ball, well, the chances of hearing a sentence like this, if 1 only refers to ball and doesn't care about the color, is going to be 1 out of 2, right? Because it could have been a red ball or it could have been a blue ball. It just so happens that this time it was used to refer to a red ball. If we get that twice, then, well, there is a 1/2 of a chance the first time we heard it, because it could have been a red ball or a blue ball, and a 1/2 a chance the second time we heard it, because it could have been a red ball or it could have been a blue ball. And the chances of hearing both of those twice in a row is 1/4. In other words, this is just like a series of coin flips. Right? Under the hypothesis where 1 just refers back to ball, and it could be a red ball or a blue ball that's being referred to, hearing like 6 instances or 7 instances in a row where it's always referring to a red ball is going to be extremely unlikely under all 3 of these hypotheses. In particular, with 6 repetitions and 2 different possible colored balls, each of these would be associated with a 1/64 chance of it being the right grammar, whereas this one is always going to be associated with a 1 chance of it being the right grammar. Now, again, in order to judge which one of these is more likely a posteriori, what the probability is after observing our data for each of these grammars to be right, we're going to have to look at the relative likelihood or the relative probabilities of each of these. Here's how that works out in the Regier Gahl approach. So now, first of all, because the other 3 grammars, the wrong ones, all make exactly the same predictions, namely that 1 can be used felicitously either in situations where it's referring to a red ball or where it's referring to a blue one, right? None of those 3 hypotheses are actually distinguishable from one another. They're all exactly the same in this theory. The only one that's different is the hypothesis where 1 has a multi-word antecedent, red ball. Right? So this one starts out being as probable as all the others. They give each of these a 25% prior probability. So they're not even assuming any strong constraints on the hypothesis space here. Everything's equally likely. The second you hear a sentence where 1 refers to a red ball in a universe with only red and blue balls, we already have a reason to favor the theory where 1 can only refer to a red ball over all the other theories. And as you hear more such cases, you become increasingly certain that 1 can only refer to the multi-word antecedent red ball, because if it could refer to any ball, then you would have expected to see lots of cases where there's a blue ball at issue or a yellow ball at issue, but you didn't. So you'd be extremely unlikely to see the data that you've seen if 1 could refer to any color of ball, but much, much, much more likely to have seen all the data you've seen if 1 can refer only to whatever color ball was mentioned in the antecedent context. So this is Regier Gahl's basic point. Look, this indirect negative evidence, if these other theories were right, then we would have expected to see lots of things that we haven't seen. That indirect negative evidence can help us learn which one of these grammars is more likely given the data that we've seen. So we could learn this kind of ambiguous fact from enough data exposure if we use indirect negative evidence as part of our reasoning. So that said, well, I think this is an interesting idea. There are lots and lots of issues with the way they present this. So first of all, here's the first mistake that they make. Here's how Regier and Gahl present the thing that needs to be acquired, the facts about English syntax that we need to get here. Uh, Example sentence 1, I'll play with this red ball and you can play with that one. So this is the kind of positive sentence that maybe children do get. It's not the lacuna sentence. This is the sentence that's going to be roughly consistent with any grammar. Here the word one refers anaphorically to red ball. This is what they say here. Anything wrong with that? Take a second here. So if you go back to the Baker presentation of this argument from the 1970s, the claim is not that in sentences like this, one has to refer to a red ball. In fact, if that were true, then it would be trivially easy to learn these facts. The claim is that it can either refer to a red ball or to just a ball. So this is, for instance, perfectly felicitous in a context where I'm pointing at a blue ball lying on the ground. I'll play with this red ball pointing over here, and you can play with that one pointing to the blue ball over there. Perfectly fine in English. The point here is that this is always ambiguous between the multi-word antecedent red ball and the single word antecedent ball. And the n-bar theory allows us to capture that because those are both n-bar level constituents in that theory. So Regier and Gahl are trying to learn the wrong generalization. So that's already a problem. That said, it's actually not a fatal problem. It would be relatively easy to fix their framework if there were nothing else wrong with it. But there are other things wrong. And so all of these counterpoints here come from the Lids and Waxman follow-up, which is on the website, including this basic fact that they're learning the wrong generalization. They've learned a grammar where one must refer to red ball. That is not English grammar. That's incorrect grammar. Okay, here's some other issues though. So Regier and Gahl's model characterizes the child's task or the acquisition task as figuring out how likely different structural hypotheses about anaphoric 1 are given some number of exposures or some number of observed situations where one refers to an adjective-noun complex, in this case, red ball. So the hypotheses here are of the form one must refer to the string of words, and the trials or the data here are uniformly cases where one refers to an object that matches a multi-word antecedent, like red ball, and by coincidence, a single word antecedent as well, a ball. So what's the problem with that? Well, think about it for a minute. This is not what the actual child-directed speech looks like. So there's two problems here. As we noted already, the actual hypotheses to be tested here include disjunctive ones. In fact, the right grammar is that one can either refer to a high or a low n-bar. And in fact, that's true no matter how many n-bars there are in the phrase. So we're looking at cases with 2 here, but the exact same thing is going to be true with cases with 3, 4, 5 adjectives in them. These facts are going to be exactly the same. The bigger point here is actually even more so than the fact that the real generalization is disjunctive. If the real generalization is an either or one, if that's the thing that has to be learned, then we need to consider as a possible grammar all of the either or statements that you could make. Right? They don't have any disjunctive grammars that they're evaluating here, or hypotheses. They only evaluate hypotheses where one has to refer to this element or has to refer to that element only. But in a more realistic simulation, we need to include things like, well, one can refer to either the head noun or the largest n-bar in the phrase, right? And that would actually get the right generalization for this very limited test case, although it would be the wrong grammar when you look at other situations and other English constructions. Right? So they don't consider these disjunctive grammars, yet if we're allowing some disjunctive grammars, one can either refer to this or to that. There's no reason why others shouldn't be included. And you can look at that and say, well, those other grammars are crazy. We just need to exclude those from the hypothesis space. Like, let's assume children don't ever consider those grammars. Right? But look at what we just did. What we've just done is acknowledging a priori constraints on the grammar that children are willing to entertain. In other words, we've restricted the hypothesis space. That is conceptually almost exactly equivalent to universal grammar. Right? What universal grammar says is that children just never consider some kinds of grammars, even though they would account for simple data. And if we want to get rid of all those extra grammars in our Bayesian approach, we're going to have to do exactly the same thing. So this is a big criticism from generativists about these Bayesian approaches where people say, hey, we're going to explain all of these syntactic acquisition data just using Bayesian inference. And the response is often, well, no, you're not. You're doing it using Bayesian inference over a highly restricted hypothesis space. Those restrictions on the hypothesis space are exactly what the theory of universal grammar is about. So let's try for a stronger Regier Gahl theory, where we actually try to do this in a more realistic set of situations with more realistic hypotheses. Let's see what happens. So the second issue here, as I mentioned briefly on the other slide, is that they're assuming that you get lots of exposures where this anaphor 1 is referring back to some kind of a red ball, and red ball was in the linguistic discourse, and you just have to decide whether it was red ball or ball given those contexts. But the input that they're assuming there, the actual input that Lids and colleagues found in the Childish corpus is radically different from what Regier and Gahl are assuming here. And in particular, we saw in that paper about 95% of the cases of anaphoric 1 occur with no multi-word antecedent at all, right? I have a ball and John has one too. So you're certainly not going to learn anything about multi-word antecedents from the vast majority of these cases. The remaining 5% of the anaphoric 1 cases are a mix of a bunch of other things, right? Mostly they're ambiguous cases. These are the ones that Regier and Gahl focus in on. I have a red ball and John has one too. So here, these are the ambiguous cases where either the one-word antecedent or the multi-word antecedent could work, and the likelihood approach, the indirect negative evidence approach, would favor the red ball interpretation in these specific cases. But this is a very small percentage of the overall cases. There's also a whole bunch of noun-only cases, right? So I have a red ball and John has one too, where I'm pointing at a blue ball, something like that. And then finally, there's a whole bunch of errors or ungrammatical sentences, as well as the lacuna, the unambiguously red ball cases. And we saw in the Lids and colleagues paper that both of those are more or less negligible. There's very, very few of either one of these, of the ungrammatical uses or the adjective noun unambiguous cases. So this is what the actual child-directed speech data looks like. And the question is, well, what would happen to the Regier and Gahl model with somewhat more realistic data and hypotheses? Now, this is not a fully realistic simulation, but it's a little bit more realistic than the one they present in their paper. And so I've picked particular ways of assigning likelihoods to different grammars of anaphoric 1 under different kinds of observations where 95% of these observations are going to be totally uninformative. They're going to be cases where I have a ball and John has one too, right? Something like that. Now, here's what actually happens in this theory. What I'm listing here in the vertical axis is the posterior probability associated with one of 10 different hypotheses. So I went to 10 different grammars here. This includes all the disjunctive grammars that you can do with the different 4 hypotheses from the Regier and Gahl paper, that it's either linear structure or hierarchical structure with this interpretation, those kinds of grammars. There's now 10 grammars, including the 4 original ones that Regier and Gahl assume. And now, instead of getting lots and lots of cases where the anaphor 1 refers back to a specific colored ball, we're getting 95% cases where there's no multi-word antecedent at all, and all of the grammars that allow single word antecedents are equally likely under those conditions. And so here's what happens. They all start out the same. I started them at 10% each, no priors on these grammars. Uh, every once in a while, so it looks like here, this is the number of observations where these are now being generated randomly. 95% of them are going to be totally uninformative, just like real life. Some of them are going to be unambiguously noun only. And then tiny, tiny, tiny percentages of them are going to be informative with regard to multi-word antecedents. For instance, the examples Regier and Gahl consider. I have a red ball and John has one too, where John's holding a red ball. Every time you get one of those informative cases, yeah, you get a spike in, presumably this is the grammar associated with you can have multi-word antecedents, and other grammars get a negative spike, right? So, that's really unlikely if you can refer to the word ball, but it just so happens to be a red ball that you're referring to. So we're getting little spikes here and little dips amongst these various grammars, but then after this trial where we get an informative situation, we get 95 more trials where we learn nothing at all about multi-word antecedents, and eventually these all settle back down towards their baseline of equal probability for each of the 10 grammars. The next time an informative case comes up, we get a much smaller spike because we now have a ton of prior evidence that they're equally likely, and so on and so forth. And this just keeps going. Spikes get smaller and smaller. This is being shown in probability relative to 0. I've put the whole scale in the graph here, and just for the sake of comparison to completely impossible. If you zoom in on the actual curve here, here's what it looks like in a bit more detail. So again, we're getting periodic spikes or dips in certain hypotheses, but as more and more and more uninformative data comes back in, they're all tending back towards their long-term average, which is going to be about 10% each, right? So this is after 100 observations of anaphoric 1. We're basically back where we started. Maybe there's a slight advantage for some of the more likely grammars over others, but this is going to be a tiny advantage, right? This would describe a world where English learners are, they don't know whether one can refer to only a noun or can refer to an adjective and a noun, but they think there's about, a 10.1% chance that it's an n-bar grammar and a 9.9% chance that it could only refer to single word antecedents. So again, this is not actually learning in any straightforward sense the correct grammar from the data. What's the upshot here? Indirect negative evidence is indeed a powerful and valuable tool for data-driven learning. I don't dispute that at all, and I don't think Lids and colleagues do either. But for syntactic generalizations, the space of possible hypotheses is so large, and the proportion of interesting primary linguistic data is so small, that many people in the generative camp doubt that indirect negative evidence could really play any useful role at all in language acquisition. That said, they don't believe that unless you severely restrict the hypothesis space. Then, of course, we're going to have very few hypotheses to consider, fewer grammars to consider in the first place. And under those conditions, you could make really valuable inferences about things that are missing from your input, right? But that only works if you severely restrict the hypothesis space to begin with, either by excluding some hypotheses from evaluation, or by adding hugely strong priors in favor of some grammars over others. And either one of those procedures is basically another way of saying there's strong learning biases or even categorical learning biases that language learners bring to the language learning task, and that's the only way they can manage to learn complex facts about grammar. That is the poverty of the stimulus argument. So that's the main content related to anaphoric 1 here. I might post up one extra lecture that takes this Bayesian approach into other domains of grammar, in particular phonology and phonetics. and shows how even there, where we're actually pretty sure that we do use indirect negative evidence, getting it to work in a manageable hypothesis space is really complicated.